Okay, so you might recognize this slide. It's because it's from the paired t-test week. So the next technique we're going to do is going to be all about paired experiments. So remember some of the examples we did with the paired t-tests. We had like a set of people. They went to kind of a weight loss camp. So we had before and after weight loss. We have somebody who rates both Coke and Pepsi. And in this case, each of our subjects in the experiment will rate both Coke and Pepsi. We're not splitting up into two groups. Some other examples. We've got a supermarket and we do a certain promotion and we look at maybe sales before the promotion and sales after the promotion. We also kind of have like, two different drilling techniques and we try these two techniques at different locations. And the location is actually the pairing value rather than the actual, say, a person. So we don't necessarily need to have people, but we usually do have people. This is the Wilcoxon, not the rank sum, but the signed rank test. And I'll talk about this in a minute. So we have got judges here, and each judge rates two products, A and B. So Judge 1 rates product A a 12 and product B an 8. These are separate judges, so there's no kind of ranking amongst product A and product B. Each kind of line is considered its own individual set of rankings. So Judge A rates product A 12 and product B 8. So the difference between those values is 4. Now, we're actually going to look at the magnitude of the difference. I'll talk about why we do that in a second. So we have the difference and we have the absolute value of the difference. So Judge 3 has a ranking as a rating of product A of 8 and a rating of product B of 9. So the difference is -1 and the absolute value of the difference is 1. So we have the difference and we have the absolute value of the difference. Note the silly mistake for Judge 5. 15 minus 12 is in fact 3, not 7. So the absolute value of the difference should be 3. Now then, with the absolute value of the differences, we basically rank these. So the lowest difference is 1, and that has a rank of 1. The next biggest difference is 2, that has a rank of 2. And then the next biggest difference is 3, and that has a rank of 3. Now, as I told you, because of this weird measurement, these are a little bit wrong. But what we do is we have all our ranks, and we have one set of ranks, but we also record which is a negative and which is a positive. So we add up all the ranks for positive values and all the ranks for negative values. So let's have a look at, I've got this in a spreadsheet with the mistake actually gotten rid of. So we have the ratings for A and the ratings for B. Now note I've actually, and then we have the difference, B minus C, and then we have the absolute value. And I've also said if the rating is less than 0, then we do a negative, otherwise we do a positive. And then note, this is a different order from the slides. I've actually ordered in order of the actual absolute differences. And then I've actually given the ranks. So we've got rank 1, rank 2. Now note, because of the we've got slightly different values because this is a 3, not a 7. We have two rankings of 3, which are both 3.5 because it would have been 3, 4. And then we have two rankings, the next lot of rankings, two values of 4. So these would be ranks 5.5 and 5.5, etc., etc. So let's just do again. Value difference 1, rank 1, difference 2, rank 2. Differences of 3 is 3 and 4, so rank 3.5. Differences of 4 are 5 and 6, so 5.5. Then we have rank 7, 8, 9, and 10. We add up the negatives, we get 11.5. And then we add up the positives, just using SUMIF. So if the value is in the F column is P, then we add it to the positive sum. Otherwise, we add it to the negative sum. So just note those numbers of 11.5 and 43.5. Now, let's just go to the actual hypotheses. Okay, so we notice, sorry, get rid of that this looks very, very similar to the Wilcoxon rank sum. We've got D1 and D2 are identical, and the D1 is shifted to the right of D2 or to the left of D2 for the one-tailed, and D1 is shifted either to the left or to the right of D2 for the two-tailed. So there's no difference in the hypotheses between the Wilcoxon signed rank test. Now, the test statistic, this is going to be T minus for kind of a right-tailed test. D1 is greater than D2, and it's going to be a T plus for the left-tailed test. So let's just think T minus is going to be D1 to the right of D2, and we're going to be T plus for D1 is to the left of D2. And again, that should be obvious that we're testing the smaller value of the rank sums. So in this case, we have our 11.5, and we have our 43.5. I'll just write that down. We're thinking, okay, in this case, kind of going back, we'll think that the positive group has a much higher rank. So, and we can count, we can see this, that, we think that group A really is going to be bigger than group B here, because most of these are probably going to be positive. So again, this is kind of analogous. Let me just get back to my screen. D1 to the right of D2. This would be for a parametric would be mu1 minus mu2 is greater than 0. Mu1 minus mu2 is less than 0. So we'd have, group 1 is bigger than group 2. And in this case, we would actually have mostly positive, so we check the T minus. But if we're looking in the other directions, we think the positives are going to be small, i.e. the non-parametric equivalent of mu1 minus mu2 is less than 0, then we're going to be having the T positives. For the two-tailed test, we just pick the smaller value. We're checking the extreme value. It doesn't matter which direction. And again, we're actually seeing if it's less than or equal to this value, T0. Okay, and I'll just kind of show you this little table here. So we have N5, N6, and we basically have some values for every kind of value of N. We also have our one-tailed and our two-tailed significance. And we basically just pick this number, this kind of T minus or T positive, T plus, and then we will do the test. Okay, so let's just go back and let's just do this test. Okay, so let's just do a two-tailed test with alpha equals 0.05. And H0 is going to be the score distribution for products A and B. And HA is going to be the score distribution for product A is shifted either to the left or right of the score distribution for product B. Okay, you get that. And the test statistic and in this case, T, the smaller of T plus a T minus, is actually going to be T equals T minus. And we're going to have the rejection region. We're going to reject H0 if T is less than or equal to T0. So let's just kind of go back to our slides. And we have, for this example, we have 10 products. And the two-tailed for alpha equals 0.05 is going to be 8. So let's just kind of go back. So we're going to reject H0 if T equals less than or equal to T0, which is equal to 8. And sorry, I'm just going to have to go over here. So calculate test statistic. We've got T equals T minus equals 11.5. So basically, conclusion, we have T equals 11.5, which is greater than 8. So we failed to reject H0. We don't have enough evidence that there's a distance between those two distributions. Okay, and just showing you, there's basically, the one I give you in the exam is basically exactly the same table. So go across n equals 10, two-tailed test, alpha equals 0.05, is a value of 8. So say, for example, we were doing a one-tailed test, we'd have alpha equals 0.05. And because of the direction we're going, the D1 is shifted to the right of D2. The equivalent of mu1 minus mu2 is greater than 0. We'd be looking at 11. So we would actually be closer to rejecting, but not quite, as the value would be 11.5. Okay, so just to summarize, this was very similar to a paired t-test, but was in fact a non-parametric version of this test. And what we're going to do next is we're going to look at an example in SPSS where we do both the Wilcoxon ranked sum and the Wilcoxon signed rank test together.